Have you ever stood on a harbor wall, looked out at a massive container ship sitting motionless in open water, and wondered what's actually holding it there? The hull alone is longer than 3 football pitches. The weight is almost beyond imagining. Wind pushes against it from one side, tide pulls at it from another, and yet the ship doesn't move. Somewhere below the waterline, a single piece of steel is apparently keeping all of that in place. It seems impossible. And in a way, you're right to be suspicious. Because the anchor isn't doing what you think it is. The global shipping industry moves over 10 billion tons of cargo every year. Every one of those vessels, at some point, has to stop and stay stopped in ports, in approaches, in storms, in waters that offer no fixed point to tie to. The system that makes that possible has been refined over thousands of years and is still, at its core, dependent on a principle of physics that most people who've seen an anchor have never been told. But here's the surprising truth. An anchor doesn't hold a ship by digging into the seabed and gripping. Not really. The anchor is almost the last line of defense. What actually holds the ship is the chain. Today, we're unpacking how anchoring really works, why dropping a hook in deep water does absolutely nothing, and how a ship weighing hundreds of thousands of tons gets that anchor back out of the mud without tearing itself apart. To understand the real mechanics of anchoring, you have to go back much further than steel chains and hydraulic winches. Ancient sailors anchored with rocks, heavy stones attached to ropes, dropped overboard to create enough drag to slow a vessel or hold it against a gentle current in shallow water. For small boats in calm harbors, it worked. But as ships grew larger and ventured further into open water, the stone and rope system revealed a fatal limitation. A rope pulled at any significant angle from the surface exerts an upward force on whatever it's attached to. Pull hard enough, and you don't grip the seabed. You lift from it. The anchor breaks free, and the ship drifts. For centuries, sailors tried to solve this by making anchors heavier, adding flukes to bite deeper into soft ground, and using longer ropes to reduce the angle of pull. Each improvement helped. None of them solved the underlying problem. Then, gradually, through the age of iron shipbuilding in the 19th century, rope gave way to chain. And that substitution changed everything. Not because chain is stronger than rope under tension, but because of what chain does when it isn't under tension. It sinks. Think of it like this. Imagine trying to hold a heavy door open against a strong wind using a piece of string tied at shoulder height. The string goes taut, the angle is steep, and the force is pulling the anchor upward as much as outward. Now, replace the string with a very heavy chain. The chain sags under its own weight. Instead of running in a straight line from ship to seabed, it curves downward and lies along the ocean floor for a significant length before it reaches the anchor. This curve is called a catenary, and it transforms the physics entirely. When a wave pushes the ship backward, the tension doesn't immediately reach the anchor. First, the ship has to lift tons of heavy chain off the seabed. By the time any force finally reaches the anchor itself, it is arriving almost horizontally, driving the flukes deeper into the mud rather than pulling them out. The chain isn't just connecting the ship to the anchor, it is the primary holding force, absorbing and redirecting energy that would otherwise break the anchor free. So if a long, heavy chain is what actually holds the ship, what happens when the water is too deep to lay chain along the bottom? The answer, as is often the case in history, comes down to the limits of the physical world. Commercial vessels generally cannot anchor in water much deeper than roughly 100 meters. Beyond that depth, the mathematics turn against the system in 2 ways. First, The sheer length of chain required to create the catenary curve becomes so heavy that the winch holding it, known as a windlass, cannot bear the vertical load of all that steel hanging straight down. Second, in very deep water, the chain's own weight exceeds the holding force it can generate because there is no seabed close enough for it to lie along and create the redirecting curve. The chain just hangs, pulling the bow downward rather than holding the ship in place. In the open ocean, where depths run to several kilometers, anchoring is simply not possible. Modern vessels caught in deep water either drift under careful watch or, in the case of precision drilling and research ships, use a system called dynamic positioning, where computers read GPS coordinates continuously and fire thrusters in precise bursts to hold the vessel stationary without touching the bottom at all. For vessels that can anchor, the crew needs to know exactly how much chain is deployed at any moment, because too little chain and the catenary collapses. Too much, and the anchor may drag across the seabed without setting properly. The solution is one of the oldest measurement systems still in active daily use on working ships. Chain is manufactured and stored in standard lengths called shackles, each one exactly 27.5 meters long. Where two shackles join, the connecting link is painted a distinct color and marked with steel wire wound around it in a specific pattern. As the chain runs out through the hawse pipe, an officer stationed at the bow counts the marked links passing by and radios the count to the bridge. The captain knows, to within a single shackle, exactly how much chain is on the seabed at any moment. The system requires no electronics, no sensors, and no power. It works in complete darkness, in heavy weather, and on vessels that have been at sea for months. It has not been meaningfully improved upon because it doesn't need to be. Breaking the anchor free at the end of a stay is the moment most people have never considered, and it is where the engineering becomes almost counterintuitive. An anchor that has set properly in soft ground can develop a powerful suction seal with the sediment around it. Simply winching upward is not enough. The windlass would stall or burn out long before the anchor moved. So the ship doesn't pull the anchor up. It moves toward it. The vessel powers slowly forward until it sits almost directly above the buried anchor. At that point, the chain, instead of running at an angle across the seabed, hangs nearly vertical. The upward pull now acts along the shank of the anchor rather than across it, breaking the suction cleanly. The crew calls this moment breaking out. The anchor lifts, trailing mud and sediment, and high-pressure water jets built into the hawse pipe wash the chain clean as it coils back into the locker below. The whole sequence is reversed from what you'd expect. The ship moves to free the anchor, not the other way around. So the next time you see a vessel at anchor and wonder what's holding it, look past the chain disappearing into the water. The answer isn't at the end of it. It's in the weight of everything in between, lying heavy and curved across the seabed, absorbing every push the ocean can offer before it ever reaches the hook. An anchor is only as strong as the chain above it, and the chain is strongest when it isn't being pulled at all,